All right, welcome. Today, we're going to pull back the curtain on the invisible force that powers, well, pretty much everything: current electricity. We're going to break down the simple, elegant rules that are running the show in the device you're watching this on right now, and even the very neurons firing inside your brain. So let's kick things off with a big question, shall we? What could a massive, chaotic bolt of lightning possibly have in common with the delicate, precise firing of a single neuron in your brain? And believe it or not, the answer is that they both play by the exact same fundamental rules of electricity. So let's figure out what those rules actually are. Okay, first things first. We've got to wrap our heads around the most basic idea here, and that's flow. But in electricity, we're not talking about water. We're talking about the flow of something much, much smaller. So we call this flow electric current, and we use the letter I for it. All it really is a way to measure how much electric charge, that's the Q, is zipping past a certain point in a certain amount of time, t. The best way to think about it is like a water pipe, you know? The current is just like measuring the flow rate. How many gallons of water are gushing by every single minute? In a wire, it's the same idea, but we're counting how much charge flies by every second. Okay, now here's where things get a little weird. And honestly, kind of cool. It's a historical quirk. We define the direction of current as flowing from high potential, you can think of that as positive, down to low potential, or negative. But here's the catch. We later found out that the actual things moving, the tiny electrons, are negatively charged, so they actually flow in the opposite direction. See, this whole idea goes way back to Benjamin Franklin, long before anyone even knew what an electron was. And even though we now know he got the direction of the actual particles wrong, his convention, it just works. It works perfectly for all the math, so we've just stuck with it ever since. It's a super important little detail to keep in your back pocket. All right, so we've got charge flowing. But here's the thing. That flow is never a perfectly smooth ride. It always runs into some kind of obstacle, some kind of pushback. And that opposition, we've got a name for it: resistance. Let's go back to our water pipe. Resistance is like a section of that pipe that suddenly gets really narrow and all clogged up, right? It just makes it way harder for the water to squeeze through. In a circuit, different materials have different levels of resistance. Copper lets electrons flow easily. Rubber, not so much. And that idea right there brings us to one of the most beautiful, most fundamental rules in all of physics: Ohm's law. V equals I times R. This simple formula perfectly connects our three main players. Think about it. V is for voltage, that's the pressure pushing everything. I is the current, that's the flow. And R is the resistance, the obstruction. It just makes perfect sense, right? The more pressure you apply, the more flow you get. The more you obstruct it, the less flow you get. It's just elegant. And you can see that relationship perfectly on this graph. For a lot of materials, if you plot the voltage you're applying against the current you just get a perfectly straight line. And the slope, how steep that line is, that is the resistance. So a really steep line means you have a ton of resistance. You've got to push really hard just to get a tiny bit of current to flow. So materials that give you that nice, predictable, straight line, like a simple copper wire, we call those ohmic. They play by the rules. But a ton of modern electronics, like the semiconductors inside your phone, they're non-ohmic. Their resistance isn't constant. It actually changes depending on how much voltage you hit them with. A diode is a perfect example. It acts like a one-way street for current, which is absolutely essential for things like turning the AC power from your wall into the DC power your laptop needs to charge. Okay, so we've got the big three: pressure, flow, and obstruction. But what happens when you start building real stuff? You know, a complex circuit board with paths going all over the place. Well, for that, you need the official rules of the road for electricity. And this is the incredible part. It all, and I mean all of it, boils down to just two really simple but super powerful rules. They're named after Gustav Kirchhoff. And with just these two, the junction rule and the loop rule, you can figure out what's happening in literally any circuit. Rule number one is the junction rule, and honestly, it's just pure common sense. All it says is that whenever wires meet at an intersection, a junction, the total amount of current flowing in has to be exactly equal to the total amount flowing out. You can't lose any charge, and you can't create it from nothing. It's just like our pipes again. Whatever water flows into an intersection has to flow back out. And then there's rule number two, the loop rule. This one is all about conserving energy. It basically says that if you start at any point in a circuit and you walk a full circle back to where you started, any closed loop, all the energy gains and losses have to cancel out. You'll always end up back at zero. It's kind of like going on a hike. You might go up some big hills and down into some valleys, but if you end up back at the exact same spot you started, your total change in elevation is zero. Same idea here. All right, so now that we have the rules of the road, let's see what happens when we use them to build things in the two most basic ways possible. Basically, there are two fundamental ways to wire things up. The first one is called series. That's where you line everything up one after another, so the current only has one single path to follow. The other way is parallel. That's where the path actually splits, giving the current a choice of different routes to take. And this is where it gets really interesting because our rules play out very differently in each setup. In a series circuit, since there's only one road, the current is the exact same everywhere. But the voltage, the pressure, gets shared or divided among all the different parts. Now in parallel, it's the opposite. The current splits up and goes down the different paths, but the voltage is the same across every single branch. And as you're about to see, this little difference has huge consequences. Which brings us to the whole reason we build circuits in the first place, right? It's not just to watch charges zip around. It's to make them do something, to put them to work. And that's where we talk about electrical power. Power is just the measurement of how fast a circuit is doing work, creating light from a bulb, heat from a toaster, or motion from a motor. And the formula couldn't be simpler. Power is just the voltage, the push, times the current, the flow. More push and more flow means more work gets done faster. So let's make this super practical. Think about a light bulb. Its brightness? That's a direct measurement of its power. So look what happens here. If you wire two bulbs in series, they're forced to share the voltage from the battery, so each one gets less power and they glow kinda dimly. But if you hook them up in parallel, each bulb gets the full voltage. They can draw way more current and boom, they shine much, much brighter. It's a perfect example of these rules in action. So let's just tie this all together. Current, that's the flow of charge. Resistance, that's the stuff that gets in the way. Ohm's law is the simple, beautiful equation that connects them. Kirchhoff's laws are the traffic rules for every junction and every loop. And when you put it all together, you get power, which is how we turn all this invisible motion into useful work. Think about it. From the simplest little flashlight to a massive supercomputer, every single one of them is governed by these same few elegant rules. They're not just laws of electronics. They're a fundamental part of how our universe works. So the real question is, now that you know the rules, what are you going to build with them?